Hello, everyone. Welcome to our paper, CausalRec Causal Inference for Visual Debiasing in Visually Aware Recommendation. This paper is done with our colleagues at the University of Queensland. Firstly, we'll talk about what is a visually aware recommendation. It's a kind of recommendation that based on visual features. For example, here is a cover page of an item, which is a white t-shirt. So we think that in visually aware recommendation, there are generally a visual bias. This visual bias means that the recommendation will be misled by visual features. Imagine when a user wants to buy a white t-shirt made of cotton, while the recommender system will recommend the white t-shirt with nylon or with fabric. So this is a kind of failure of recommendation, since the user wants a white t-shirt made of cotton rather than other materials. So in this paper, we propose to use the causal inference to do the debiased method. So firstly, we introduce what is causal inference. For example, here is a causal graph. This graph includes 3 nodes and with some edges indicates their causal relationship. For example, A is the cause of both B and C, and B is also the cause of C. So this assignment of A equals lowercase a means that we want to assign A equals A, and it will affect the node B and node C as well. Well, for figure B here, we assign another different values to A, which is the A asterisk. In this paper, we say that this kind of assignment means that it is no treatment. And while for figure C and figure D, we introduced that this is an important concept called intervention. We divide the node A into 2 nodes and then assign different values for this node A, and we will combine the final result of the how A affects the causal effects of node B and node C together. And we can see that these are 2 different types of assignments after the intervention, and it will provide a different result for node C. We can see from this subscript here. So we also introduced 3 important causal effects here. The first one is the total effect. It's calculated based on the subtraction between the assignment of A equals lowercase a and the A equals A asterisk. And also we introduced the natural direct effect, which is calculated between figure D and figure B. So it's also a subtraction of these 2 final results of C. And we finally introduced the total indirect effect, which indicates the total indirect effect of A over C. And it is calculated based on the previous 2 terms, and we use total effect minus by the natural direct effect. And we can see its final formula is like this. And we firstly use the causal graph and causal inference to analyze the existing models. For example, for matrix factorization, it's a method using the user information and item information together to do the final calculation of the prediction. So in this figure, we introduce 4 nodes. The node I indicates the item, node U indicates the user, and the node M, which indicates the preference matching, and also the node Y, which is the final prediction. So we can see that the preference matching term is based on node I and node U, which is corresponding to this term. And then the final prediction is based on these 3 nodes. And so it is these 2 bias term and the preference matching term. So this is another bias in the model that we don't care about in this method. So for the visually aware recommendation baseline VBPR, it's quite similar to the matrix factorization, except that it has an addition term for visual features here. So in this term, it's based on the user information and the visual feature. So we add this right part to the figure, and then the node V indicates the visual feature, and the node N indicates the visual notice between the user and the visual feature only. And its final prediction result is calculated by these four terms, since we just have a addition visual notice term compared with the matrix factorization. Well, for the other two baselines, deep style and AMR model, they're quite similar. We can see that in their causal graph, it is also quite similar to VBPR, except that they don't have the direct causal effect for node I and node U towards the node Y. And this can also be seen from their formulas here. They just have a user term, and this user term is multiplied with the visual term and the item term here. So they don't have any bias term, which indicates the direct effect of the node I and node U towards node Y. Well, for the other DVBPR method, it is more like only using the user information and the visual information of the item together to do the prediction preference. So they don't have the left part here because they don't have any preference matching between the user and the item. It can be also seen from this formula. So how do we define a visual bias in this method? So remember our question to whether recommends white t-shirts of different materials to a user who wants a cotton white t-shirts. The answer is definitely no. But usually the recommendation will do so because they will have the same visual feature, and this recommender system will just recommend these t-shirts to the user. So how to deal with this problem? The basic idea is to remove the direct visual effect, which is defined as the visual bias in our model. And this is introduced by the causal path like this. It's from node V to node N, which is the visual notice, and finally towards the preference calculation. But we still want to retain the indirect visual effect of the visual. So we want to use the visual feature in the preference matching term, and then using that visual indirect effect to calculate the preference prediction. So the mathematical representation is to use the total indirect effect, and the final formula is like this, and we'll look into it in the next slides. So for existing models, we want to debias. So how do we debias? For example, in VBPR, you firstly do an intervention in its node I, and then assign different values to this left part and right part. So on the right part, we assign the original visual feature to the model, and then we want to do the subtraction between these two graphs. And in this method, and we can subtract the direct visual feature from the original prediction. So this is how we do the visual debias in VBPR. Similarly, for deep style or AMR method, we also do an intervention on the node I, and then assign the original visual feature to the visual notice causal path here, and then do a subtraction between these two causal graph, and we can finally have the debiased result for this method. So in addition to analyzing the existing models, we also propose a new CausalRec model. So remember that we want to introduce the visual feature into the preference matching term. So this is how we do that. We add an extra edge between the node V and node M. And then we propose three submodules to related to the matching between user and item, and a matching between the item, its visual feature, and the user, and also the direct visual notice between the visual feature and the user. So for debiasing, we still do the intervention of node I, and when we divide the node I into two parts, the visual feature is still, or the original item is still used to calculate the visual notice for the final preference prediction. And then we want to subtract between these two graphs. This is how we do for the total indirect effect to calculate how much visual feature we want to use in the preference matching term on the left part here. And its formula is like this. And we can notice that we use a lambda2 to control how much visual bias we want to subtract from the original prediction, and it can control the scale of the visual bias. And the training objective is to train using the recommendation recommendation loss to train on the final result and each of the sub-modules here. So I'll look into the experiments. We use 8 subcategories of the Amazon dataset, and we use these metrics to evaluate our model. Also, baselines are introduced in previous slides, the BPR, VPR, and the AMR model. One thing to notice is that the setting is using the implicit feedback, which is not a perfect environment for the debiasing method, as indicated by the reference 6 here and also by the reviewer of our paper. So firstly, we look into the overall performance. CausalRec can generally outperform all the baselines method. And one thing to notice is that some visually aware recommendation baseline cannot always perform well on every dataset. We can see that VPR sometimes perform even worse than BPR in this dataset and also in this dataset. However, our CausalRec can consistently outperform these baselines. And when looking to the causal inference, we add the causal inference to debias for all the baseline, visually aware baseline method, and also in our CausalRec, we can see that for the blue bars, which indicates the method without the causal inference, they always have lower performance. While if we add the causal inference to do the visual debiasing for this method, the performance can be improved consistently. And also using the causal inference will not increase the number of parameters or the runtime of the testing. And we remember that in our final prediction formula, we have a hyperparameter lambda2, which is used to control how much bias that we want to remove in our initial prediction. So we can see that in these two figures in the x-axis, it indicates the scale of the lambda2. And in some specific scales, when we remove a specific proportion of the bias, the performance can be improved. Well, if we remove too much of the bias, the performance will become so bad. So there is a appropriate proportion of the visual bias that how we want to remove in our initial prediction. So in conclusion, in this paper, we analyzed the visual bias using the causal graph and the causal inference. And then the debiasing for this visual bias is proposed based on the causal inference. We also propose a novel CausalRec model for visually debiased recommendation. And from the experiments, we can see that the causal inference-based debiasing method can effectively debias for this visually aware recommendation. And here is the reference. And thank you, everyone.